So for recording purposes, today is heat part 4. And here's what I need for you guys to do, right? I need you to just draw a simple diagram here. I need you to take down this little note on top. I will explain it in a little while, but it's pretty self-explanatory. Energy lost in a system is equal to energy gain, meaning that if something loses 20 joules of energy, something gained 20 joules. It's like if you lost $50, that means somebody found that. Well, we'll eventually find it and gain $50. Energy lost is always equal to energy gained. And just knowing that concept, you can build an equation that allows you to solve something. And then take down this here, right? The information to the top, you should already have that from previous questions. When you finish, take down everything I ask you to take down. Just let me know, and we will do this question together as a team question. So people like when you're given a question, they like to give you the values of certain things. Like the specific heat capacity of water, the W is for water here, is 4,200. How did scientists figure that out? They must have done some sort of experiment to know that value in the first place. Different metals like silver and gold, and let's call one more, let me just call lead. Each of them have a different specific heat capacity value. They even have different specific latent heat values. The point is, to know the specific heat capacity value of a substance, scientists just don't pull it out of thin air. They must have done a certain experiment to figure it out. And that is what today's question is about. This person here is making a hammer. So the hammer is made up of a certain metal. The question didn't say what the name of the metal is. It could be iron, it could be silver, it could be lead. Well, we simply just don't know. But the point is, the specific heat capacity of M, I put an M for metal, the specific heat capacity of this particular metal, we simply don't know it. And that's the aim of the question, to find the specific heat capacity of that metal. Now, in all systems, right, if something loses energy, something will gain energy. Here we have water, right? The water, the amount of water it's clearly stated in the question. You have half a kilogram at 27 degrees Celsius. And then you have the metal, you have 800 grams of it at 150 degrees Celsius. And look at the temperatures, and the temperatures make a difference. The metal is 150 degrees Celsius. The water is just a mere 27 degrees Celsius. Using a little bit of common knowledge, do we all agree that if you dip this hot piece of metal into the water, right? What will happen to the temperature of the water? Right now, the water is 27 degrees Celsius. If I dip that in the water, will the temperature of the water go up or will the temperature of the water go down? Think about it and I'll say it back. If you dip something hot into water, what does common sense say? Will the temperature of the water go up or go down? Right? The easy question. I don't think it's a trick question, right? Right, and common sense will say that the temperature of the water will go up. Now, it actually kind of states that in the question, but the question really not supposed to tell you that because that's common sense, right? Look at it. The water was 27 degrees Celsius, and at the end of the experiment, the water went up, right? To 55 degrees Celsius. So that shows that the temperature of the water went up. And common sense will say that the temperature of the metal will go down because when you dip the metal in the water, it will begin to cool off the metal. Now, here's the thing. At the beginning of the experiment, both items are at a different temperature. The metal is 150, the water is 27. But bet all your money, at the end of the question, the two of them will cool down to a common temperature. And that common temperature is 55 degrees Celsius. So at the end of the question, both the metal and the water will meet and settle on a common value. You call that the equilibrium temperature, right? So just note that, and just note this at the end of the question. At the end of the question, the metal is 55 degrees Celsius and the water is also at 55 degrees Celsius. Once again, that term is the equilibrium temperature. Quick question. Who is losing energy and who is gaining energy? Is the metal losing energy or gaining energy? And I want you to answer the same question for the water. Is the water losing energy in this experiment or gaining energy in this experiment? Think about it and send your answer on it. Remember, the metal is hotter and it's cooling down, and the water was colder and its temperature went up. Hotter things have more energy than colder things. So the metal is losing energy. Remember, the hot metal is giving its heat to the water so the water may rise in temperature. So the metal is losing energy and the water is gaining energy. Now, keep in mind, it's this formula we have to use for the experiment. It's not this one. How do I know it's that formula that we're going to end up using? Because wasn't a piece of metal a solid at the beginning of the experiment? And at the end of the experiment, it was still a solid. There was no change in state with the piece of metal. And the water, as far as I could tell, the water was liquid at the beginning of the experiment. And at the end of the experiment, it's still water. There is no change in states. It seems that in this experiment, it only have a change in temperature. So it's the red formula. Keep in mind, the energy lost is equal to the energy gained. So in other words, remember we said, and we agreed on, the metal is losing energy. So the energy lost by the metal is equal to the energy gained by the water. You can create an equation out of this now. So here's what I want you all to take a try now. Take it from here. Create an equation that tells you how much energy the metal is losing. I'm giving you a hint, is this formula. And put it equal to the amount of energy the water is gaining using the same formula. Put the two things equal to each other, and you'll have a simple algebra equation that allows you to solve for what the question is asking, which is the specific heat capacity of the metal. Just take a try. You don't have to get it correct. Giving you a couple minutes, right? You'll be surprised of how much of you all will come close to getting this out. Okay. Small little trick, not a big trick. You notice that the specific heat capacity values are using kilograms, right? So the small trick is the mass of the metal is given in grams. So I try to trick you there. You need to convert that to kilograms before you start the question. So you divide it by 1,000, and anybody can do that and give you 0.8. Yeah. So here's what I'm going to formulate, right? Energy lost is equal to what? Energy gained. So who is losing energy? I'll put M for metal and let's put W for water, right? So to make it easy. To calculate the heat energy lost by the metal, you use this formula. You're going to take the mass of the metal. We're dealing with the metal, energy lost by the metal. So everything has metal values. The mass of the metal multiplied by the specific heat capacity of the metal, which we don't know, multiplied by the change in temperature. The change in temperature of the metal is not hard to calculate. If it started off at 150 and it went down to 55, and to find the change in temperature of the metal, we just have to take 150 and minus 55. Minusing the 150 and 55 will give us the change in temperature. So let's put that formula here. The values. The mass of the metal is 0.8. The specific heat capacity of the metal, I put a little m here so we know it's the specific heat capacity of the metal, which we don't know. And how much is the change in temperature? Let's take 150 and minus 55. I get the change in temperature to be 95. So now who is gaining the lost energy? It comes like the metal donating its energy to the water. And the water say, thank you for that energy. So let's do the water now. The heat energy that the water is gaining is the mass of the water. Well, the mass of the water is 0.5. We know the specific heat capacity of water that was given is 4,200. And how much is the change in temperature of the water? The water started off at 27 and went up to 55. If you're minus 55 and 27, I get in 28. You could take it from here, guys. You could solve for this. Use your algebra skills to find the specific heat capacity of the metal. And once you solve for that, you're finished. That's the end of the question. Right? You're actually supposed to do this experiment in school. It's supposed to be one of your SBA labs. All right, guys. So you have the 0.8 and the 95. You can multiply those two things first, and then you can multiply out this side. So you can simplify it using your, algebra skills. 0.8 by 95 is 76. 0.8 by 95, and then you multiply these three things here. 0.5 by 4,200, that's what? 0.5 by 4,200 by 28. Right? Now, if you get 58800, you're on the right track. But you can't suggest that this is the final answer. I can't imagine why somebody would stop at that point and claim that is the final answer. I mean, remember, you're trying to solve for the specific heat capacity of the metal. You need, like, if you're trying to solve for X, right? That means you're trying to get X on one side and everyone else on the other side. So you have a big piece outstanding. The 76 is a multiply, throw it across, you get what? A divide. So if you divide it, you get 773.68. If you go to two decimal places and get the units, joules per kilogram degrees Celsius. So the specific heat capacity of that mysterious metal is 773.68. Try this question now. Here you have, it's almost the same thing, right? But you see how the last question, right? Now sorry, it's a little bit harder. Yeah, but everyone draw the diagram, and I'll add a set you up for this question. This one a little bit harder than the previous question, but it's still the same concept. Energy lost is equal to energy gained. The lake, it's not said in the question, right? But you got to use a little bit of common sense here. And the examiner will be more clear than me. But if you see a lake of water and it's starting off at -5 degrees, doesn't that suggest that it should be ice at the moment? Because water freezes at 0, right? So, but the examiner would make it more clear in the exam, in his wording. He will say that there's a lake, it has 8 tons of liquid, water or whatever, ice in it. He will say it have 8 tons of ice in it, and the ice starts off at -5 degrees. And at the end of the experiment, when the comet crashes into the lake, the temperature of everything levels off at 11 degrees Celsius. That means the comet at the end of the question reaches 11 and the ice warms up to 11. Now, if something starts off at -5 degrees, I'm talking about water, it starts off at ice, and then when it's 11 degrees, it's now water. So to me, there's a change in state. There's plenty of things going on in this question, right? Somewhere along the line, there was a change in state. There was. So my question to you is this: who is losing energy and who is gaining energy? Is the comet losing energy or gaining energy? And I ask the same question for the water. Is it losing energy or gaining energy? Let me know in the chat. Let's first make that distinction before we do any calculation. From here, right, I'm telling you which formula it have, right, to use for each case. Now, it have two formulas. It have the red one and it have the blue one, right? The blue one is the latent heat and the red one is specific heat capacity. So I'll let a color code in it for you, right? To calculate this portion here, you need to use the red formula. So I'll put in a red dot for this portion here. When it goes from ice to water, there's a change in state. So you're using the blue formula. And then from water to water, no change in state, but a change in temperature, that will be which formula? The red formula. So I've given you an idea. Make sure you use the correct values. It have specific heat capacity of ice, it have fusion, latent heat of fusion, right? Anyway you see W, it's for water. Well, I write ice for ice, but most examiners won't spell out the word ice. They will use just the letter I to represent ice. Right, so that's some hints there. I hope it helps. Any parts, right? For this red part here, we're using the red formula, right? So the mass of the ice is 8,000. Look at there. Because I'm using it, I have the color coded. Now we're dealing with ice. The specific heat capacity of ice is 2100. And how much is the change in temperature? The ice going from 5 to 0. That's a change in temperature of 5. You just take the positive version. So 8,000 by 2100 by 5. A huge value. It's 8, 4 with how many zeros? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 zeros. 1, 2, 3, 4, 5, 6. How much people have up to there correct? Like somewhere you're seeing 84 million. That means you're on the right track, right? I'm not rushing you. Go ahead. Second part, the blue formula. Remember this formula here. So the mass is 8,000 and the latent heat of fusion of water. Now, when you say fusion and water, that means it's changing from ice to water or water to ice, right? Fusion is for melting scenarios, from liquid to solid or solid to liquid. And we have a huge value there, right? 334 with 3 zeros. Oh, Lord. I don't know why I use that such a large. Good. We get in 2, 6, 7, 2 with how much? 1, 2, 3, 6. 1, 2, 3, 4, 5, 6. I'm hoping you're seeing that somewhere in your calculations. For the red part here, right? It going from 0 to 11, that's specific heat capacity. And right now it's water, right? So for this calculation here, it's using this formula. The mass is still 8,000. Specific heat capacity of water is that. And how much is the change in temperature of the water? It changed by 11, right? Because it went from 0 to 11. 8,000 by 4,200 by 11, wait, 3696 with 5 zeros. 1, 2, 3, 4, 5. How much people have all of those values? I'm going to have to erase this, so make sure and take it down. So this is the energy gain by the lake. Obviously, to get the total energy gain, we have to add up 1, 2, 3 answers. Right, so I'm just going to take my time and add up these three things. 2, 6, 7, 2, 1, 2, 3, 4, 5, 6, plus 8, 4, 1, 2, 3, 4, 5, 6. This is what I get if I'm writing the value up here, right? So 3, 1, 2, 5, 6 with 5 zeros. 1, 2, 3, 4, 5. How much people could confirm that the right-hand side work up to that crazy value, right? I mean, your calculator doing all the hard work, right? You just have to take your time and type it in, right? That's all you have to do, right? Right. It just sometimes under pressure, you just get the amount of zeros wrong now because when you're under pressure, you gotta write all of those zeros. 5 zeros, it look like 6 zeros, right? So, but you gotta take your time, count it out, put your finger on the calculator and count the amount of zeros. Right. Let's create a full equation here, right? The energy gain, we now calculated it. Let me write it in. The energy gain was 3, 1, 2, 5, 6 with 5 zeros. 1, 2, 3, 4, 5 joules. What's the energy lost by the comet? The mass of the comet is 5 kilograms. So using this formula, the specific heat capacity of that comet, we don't know. I put C for comet. We don't know that. That's the aim of the question. And how much is the change in temperature? Remember, everything leveled off at 11 degrees Celsius. So that means the comet started out at 2000 and ended up at 11. That was the equilibrium temperature. Once again, the equilibrium temperature is the temperature everybody, the final temperature of everybody in this scenario. So 2000 minus 11, at this point in here, I know a few people will ask, 2000 minus 11 degrees Celsius is 1989. So solve for the specific heat capacity. I'm going to multiply the 5 by this. You're going to get 9945. Well, I multiply the 5 by the 1989 specific heat capacity of the comet. It's equal to 3, 1, 2, 5, 6, 1, 2, 3, 4, 5. And we want to solve for the specific heat capacity of the comet. Draw across and multiply. You're going to get a divide. So the specific heat capacity of the comet is 3, 1, 2, 5, 6, 1, 2, 3, 4, 5. I'm getting this. Anybody could have, not everyone got this. I guess it's because the amount of zeros now, people just missing so many zeros. I get in 3, 1, 4, 2, 8, 8, 0.59. If you go properly to 2 decimal places, joules per kilogram degrees Celsius. Who could agree with that? Right? Right, people are getting it. Good, good, good. Right. So there's some mix-up questions here. Here we have a strange question. I want you all to let's just work out this one together. I doubt you're going to be able to draw this diagram here. You're also supposed to do this one in as a lab. here's what you have in this question. Let me just explain. You know, sometimes you could use electricity to heat up things. You just do it all the time, and you have an electric shower at home, an electric heater system. We use electricity to heat up water. What about the water kettles that you use to make tea and coffee with? And it is use electricity to heat up the water, right? So the point is, you can convert electrical energy to heat energy. And once again, energy lost is equal to energy gain. So let me just explain this question because it might be kind of hard to see. In the lab, your teacher is supposed to give you a piece of metal. I just shading the metal here because it might be kind of hard to see, right? Shading the metal here. And the metal will have some holes drilled into it. The examiner will do that already. One hole is to dip a thermometer in. The reason is you need to measure the temperature of the metal. So they just drill a little hole for the thermometer to fit in snug. So it will measure the temperature properly. And then you're going to use an electrical heater. And the electrical heater, this is it here, by the way, I put it in pink. You drill a hole for the electrical heater to fit in. And the heater is going to heat up the piece of metal. And it's going to be like a mysterious piece of metal. So you won't know the heat energy. Sorry, you don't know the specific heat capacity of the metal. The aim of the experiment is to find the heat capacity of the metal. So I'm going to give you all some formulas. Now, this will only make some sense if you did the electricity homework, right? Remember, I have this formula, work or energy. Work and energy is the same thing, right? Work is measured in joules. It's power multiplied by time, but the time has to be in seconds. Power, there are many ways to calculate power, right? Many ways. If you look back in your notes with electricity, one of the ways to calculate power is to take current and multiply it by voltage. So all you need to do is come up with a formula with the amount of electrical energy that is being used in this scenario, and that is going to be transferred to the metal. So the electrical system is losing energy, and who is gaining the energy? The piece of metal. So once again, energy lost will be equal to energy gained. Using this diagram, like I said, I don't expect you to draw it. It's too complicated. I want you to find the specific heat capacity of that piece of metal. Also, please don't fall for the trick. The weight of the metal is in grams. Just make sure and convert it to kilograms. Take a few minutes and see if you can get out of this question. The electrical energy is the energy lost, and the metal is gaining that energy in the form of heat. Because, like I said, electrical energy can be converted to heat energy. Losing, right? Remember, work and energy is the same thing. All you have to do is take the power and multiply it by the time. The time has to be in seconds. So make sure and convert this 10 minutes to seconds. Also, to calculate the power part is just current by voltage. I give you the voltage here, but the amps I give is not 20 here. I give it in milliamps. So you have to divide this by 1,000 first. Milli means divided by 1,000. So make sure you convert, when you divide it by 1,000, you'll get this amount of amps. Don't get fooled by little small tricky units. The examiner will do things like this. Put things in the wrong units, and you have to convert it to the correct units. Okay? Keep going, keep going. These are little hints to kind of push you. Let's see if you got the energy calculations correct. I'm doing it to the side here. Remember, to calculate the work or energy, remember energy and work is the same thing. You have to take the power. Power is current by voltage, like I said, and you're going to multiply by the time. The current is 0.02, the voltage is 24, and the time is 600. Like I said, every minute has 60 seconds. So you had to convert it to that. How much people got this for the first part? 0.02 by 24 by 600. The energy being provided or lost by the electrical system. I got a real small answer though. Anybody get 288 joules? Real small answer there, but yeah, that is what I am getting. Anybody else can agree? Right, people are getting it. Right, so that is the energy lost. Calculate the energy gain now. Who's gaining the energy? The piece of metal. You're using a red formula. Well, it's not on this slide, but because it's a specific heat capacity question. There's no change in state here. It was a piece of solid metal at the beginning of the experiment, and it remained solid at 42, right? It just changed from 27 to 42. And the answers are popping up, but I'll still give you all some time. All right, so let's see here. The mass of the metal is the mass of the metal, you gotta divide it by 1,000, right? So it's 0.35. We don't know the specific heat capacity of the metal and how much is the change in temperature. It went from what? 27 to what? 42. 42 minus 27. I get the change to be 15. So that means if I multiply this and this, 15 by 0.35, I get in 5.25 by the specific heat capacity of the metal. So this here represents the energy being gained by the metal, and that should be equal to the energy lost by the electrical system. So it's just to solve. Throw across and multiply, bam, you get a divide. Let's see what we get here. 288 divided by 5.25. Hey, you're getting the answer a lot of people are submitting. 54.86 joules per kilogram degrees Celsius. Just double checking the answers on the chat here. Am I seeing correct? So it's 54. The decimal place is here. And it might just be a typo. Some people put the decimal place after the 8 by mistake. But let's double check it now. It should be 54 point something. Once again, lots of people getting the units wrong. We're trying to find the specific heat capacity of the metal. Last time I checked, specific heat capacity is joules per kilogram degree Celsius. You can't mess up those units, you're going to lose real plenty marks in the exam. That could actually, you could do everything correct. If you put wrong units in the exam, like you do all the calculations correct, you get all the theory correct, but you get the units wrong in every question, I guarantee you, you won't get a 1. You'll come out with a 2.